Hello, this is Semantic Web Technologies, Lecture 3, Semantic Web Basic Architecture Part 2. Today, we want to talk about how RDF and RDFS data are stored in databases. So you have several possibilities to do that. You know that RDF graphs can be represented as a set of triples, as subject, predicate, object. And of course, these sets can simply be stored in a relational database management system. For example, in a single table where you have a column for subject, a column for property, and a column for object. So why not doing that? That is quite a good idea because for relational database theory, there is a 40 years experience in research there. So this seems to be a good idea. The only thing we have to do is, okay, somehow we have to convert the Sparkle queries that we have formulated into SQL queries with respect to the given schema. And on the other hand, okay, we then can make use of the relational database system to answer the SQL query that we have converted. And in the end, we have to generate the Sparkle results from the resulting SQL results. So this is a common way, for example, to engage or to implement Sparkle on the base of relational database technology. You can do this quite in a different way. For example, you can also make a Sparkle endpoint on top of a graph-based database. But this is something different. What we want to look into today is how can we do this on the top of a relational database management system. Okay, traditionally, there are 4 ways to do this or to encode RDF triples within relational databases. First thing is we can use a giant triple store. We'll go into detail soon after. Then we can use so-called property tables. We will have a look at vertically partitioned tables, so-called binary tables. And in the end, I will show you what can be understood under a Hexes store. Okay. First thing, giant triple store. So pretty simple. We take every single triple into one single table. And in the table, we have 3 rows, 3 columns. We have subject, property, and object. And of course, this is easy to implement. You only have to implement one table within the database. And then, of course, you have lots of different properties in the property column. But of course, to access this, the problem is, okay, you have to do lots of self-joins on that relational database table. And also for that reason, your indices, they have to be chosen with care to enable efficient computation inside a giant triple store. So, for example, what we have to do now is we have to translate a Sparkle query into SQL. And as you can see here, it is pretty simple. Here, what we do here is we want to select universities where we have grad students that have bachelors from the same university. So this is quite simple, and we can select this, of course, in SQL. And as you see here, because we select 2 different graph patterns, we have to make a self-join on this single table, and we have we select here triples from T1, and we select triples from T2. So we have twice we select from this table. And in the first hand, we want to take out all rows that have the type grad student, and we want to combine that with here the bachelors that have the bachelor from the same university. So this, in that sense, you can translate a Sparkle query into a SQL query. The problem with that is only that you have one self-join, and if you have lots of conditions and lots of graph patterns, you will have lots of self-joins, and this, of course, leads to a blow-up in computation, and of course, this will take a while. So you have to think of some better ways to encode your triples in RDF with relational databases, and also maybe to transform your Sparkle queries to SQL queries. Okay, one thing to make this a little bit more efficient is, okay, I do not always have to use in my triple table the full URIs, which takes lots of space. And simply for reasons of efficiency, I can have a translation table where I have the name or the URI of the thing I'm talking about, and I use some index or I use some ID to qualify that URI. And then simply I have a table that is filled with IDs, and this is of course much shorter, and to interpret the idea then I have to rely on this translation table. But on the other hand, this is much faster if I do not have to make large string comparisons for URIs. If I can, for example, here deal with numericals, then it's much faster, the computation. And on the other hand, if I want to deal with multiple RDF graphs, with different RDF graphs, of course, I need an identifier that says which kind of or which graph I'm accessing to. So I'll end up not in a triple store, but in a quadruple store. And in a quadruple store, for example, you also have an identifier everywhere that says that this triple belongs to a specific graph. So you have here some provenance information that is given in a quadruple store. Okay. But up to now, we are just dealing with a single table that has subject, property, and object in it. So the idea is pretty close or pretty near that, for example, why not splitting up this table in several tables to make the queries more efficient and to avoid the computational overhead that is produced in these self-joins. Okay, the first idea is I try to aggregate properties for similar subjects in n-ary tables. Here, for example, I can identify from the table I had given you before, there are professors and there are students. And of course, they have different properties, but I can aggregate all professors and all students in one single table. Of course, then you need fewer joins. But on the other hand, doesn't this look like a relational database table? Of course it does. So the problem only is that in a table like this, and if you have given everything as an RDF database, you in many times will have a null in one of the fields that is available here, because for all possible property, you have another column. But of course, you do have to do some kind of clustering. And this clustering to select all similar subjects, this is not a trivial task to do. So this is pretty much complicated, and it's most times performed by hand. And then if you have multivalued properties, okay, it becomes difficult, because if you have multivalued properties, then you will have several rows for one and the same item or entity, and this makes complexity here even worse. So the other idea is quite reverse. We say, why not making a table for each single property? And then for each property, sum up all subjects and objects that are related to that property. So this is pretty simple. This can be done by machine. So you do not have to do an intelligent or smart clustering for that. Of course, this form then also supports multivalued properties. You will have no nulls in it, because if there is no property for a given subject or no object, then you don't have a row in these tables. So it's pretty simple. And you only have to read here the attributes. So you only have to read the attributes that are really needed, so you have less I/O. So less I/O, no clustering, no nulls, and you have excellent performance when you have only a small number of properties. It's fast if you want to access a specific property, because then you know which table to access. But when you have a query that is on arbitrary properties, so a query on unbounded properties, then you have to access probably all tables that are in your database, and this, of course, will be quite expensive. So there are always some advantages and disadvantages that have to be weighted out. So how do you really store these different things then in a real file. So you have, for the relational database, two different versions. You have row-based storage and column-based storage. And in the row-based storage, what you do here is you store each tuple consecutively. Each tuple will be stored consecutively in the table. Then, of course, you have to read an entire row. You have to read entire rows when attributes have to be projected and you only require one value or one attribute. So this might be an overhead. On the other hand, if you use column-based storage, then it's pretty simple. Then you have the tuples aggregated in columns within your file, and then projection, of course, is for free. And you can only read one of the columns, and then you have all values that belong to a specific attribute or specific property. What is expensive here in the column-based storage version is, of course, the insert, because if you insert new triples, then you have to match the right column for the given property to support this column-based storage. So both of them have advantages and disadvantages. Another way to organize triple stores are the so-called hexa stores. There, you create an index, or you create every possible index for each combination of subject, property, object to enable most efficient processing. So you have on the one hand an index on SPO, which combines subject, property, object. Then in the reverse direction, you have for property, object, subject, for object, subject, property, and so on. So in the end, you have at most 6 different versions of an index, and each single index is organized as you see here. You have one subject, and one subject key points to a sorted vector of property keys, and each of these property keys points to a linked ordered list of object keys. And what you do here is, of course, these list of object keys, so the end lists here, they can be reused for the other or for one of the other indices. So this is a little bit more efficient. So if you organize your index in that way, then you will have fast access. So as you can see here, you can do fast joins when there are indices for each single combination available. But on the other hand, of course, this costs you a lot of storage. At most 5 times as much storage as originally is necessary to make these 5 additional indexes. It's clear. And of course, because this is huge, when your main memory is consumed and the indices do not fit into your main memory and you have to access the disk to switch to another index, then of course this will slow down the performance of your triple store. So these are different ways to implement triple stores, and I'm sure there will be new ways with different kind of databases ahead. But you can try out several existing triple stores, and you can also make comparisons with their performance. For example, the Apache Jenna works together with the Jenna framework for RDF, and there you have an API that you can use, and you can set up a triple store, and you have also a programming interface to use this triple store, not only with a Sparkle endpoint, but also from a program. And one of the best-known triple stores is the OpenLink Virtuoso. It's a very large triple store for large databases, and it also can be combined with a regular traditional relational database that is also available from OpenLink. Sesame is another interesting triple store, pretty simple to implement. Swift OLIM, also for there is a version of this OLIM called Big OLIM, which is for large triple knowledge bases. Allegrograph is another example. So if you want to have an overview which triple stores are available, the W3C maintains a list of triple stores that's always up to date, and there you can find all the triple stores that are available and that you can try out. Some of them are for free, they are open source. Others need commercial licenses to be purchased. Okay, so this is how RDF triples are stored in databases. What want we do next? So the problem is, up to now we only know RDF and RDFS for knowledge representation, but is there more in the world than RDFS, or do we require more to formulate or to represent more complicated knowledge? So this we will look at in the next part of the lecture, when we will deal with the limits of RDF and RDFS.